Hello everyone, this is Human Hard Drive, and today we're continuing on with our AVR-C tutorials. Today what we're going to be doing is we're going to be talking more about the three registers I had introduced last time. Remember that those are the DDR register, that's the direction register, the output register, and the input register. Today what we're going to be doing is we're going to be using a tactile switch to control this LED. So, what I've got here is just a simple tactile switch. Good idea to probably get one of these for the project. What we're also going to be talking about is we're going to get into not Boolean, binary operators. So like our AND, or XOR, all those operators. So again, this is probably going to be another long tutorial, so just bear with me, and I promise it will be worth it. So what I'm going to do is I'm just going to go ahead and take this switch and plug it into, I'm going to take the breadboard first, and just go ahead and plug it into the breadboard. There we go. Now the thing about tactile switches, I'll pick this up first, is that by pushing the button, it's actually connecting the two diagonal pins. So here, lower left, upper left, lower right. And if you're not sure about that, if you ever forget, it's never a bad idea just to bring out your handy-dandy multimeter, set it on continuity. That's the mode where if you touch the two probes together, it beeps. Touch the pins you think will do what you want, push the button. Good noise. And looks like we were right. Alright. So I'm also going to assume at this point you understand the hazards of using a button improperly. If you don't know what I'm talking about floating pins, leaving things unattached to either high or low states. If you're interested in that, I'll post a link to a video I made down here. But what we're going to do is we're going to enable pull-up registers in our code. So that's going to set the pin at a high state. So what we're going to do is we're going to need to connect the switch to ground. So I'm going to go ahead and take the lower left, connect that to ground, which I have attached to the LED. And I'm going to take the upper right, find out where that is, there it is. And I'm going to attach it to the pin we're going to test. I'm still going to be using port B, so we can recycle the code we used from the last video. And I'm going to go ahead and connect it to pin 15, which is the pin opposite the LED control pin. So it's right next to it. I've got my data sheet open. Always a good idea to have your data sheet open for this chip when we're going to be doing this stuff. So there's our circuit. Let's go ahead and look at the code. Alright, so before we get started on the code, I just wanted to make sure you understood that here's PB0, that's the pin controlling the LED, and here's PB1, the pin that's going to be receiving data from the switch. So, output, input. Great, good, onto the code. So what I've gone ahead and done is I've created a new project in AVR Studio, Switch LED, and I've just copied the code from our last project, recycling old code, always a good idea, and I've just put it in here, so everything's exactly the same, so all we've got to do is tweak this to make it work. So I'm just going to go ahead and delete this stuff out of the main loop, because that's what's going to change. Let's start by tweaking DDRB. Now that's the direction register. Sorry. So that's the direction register. Now we set PB0 as an output, because you can tell, because if you remember last time, or because you recognize that the 0th bit in the DDR-X register is 1 or 0. And since this is 1, and when you put 1 into the DDR-X register, it becomes an output, well,
There you go. So it's going to stay the same because if it's a 1, it's an output, and since that's the only 1 in the register, everything else must be an input. Great. Now, port B. I told you we would have to enable the internal pull-ups. So in order to do that, normally the port B, it turns on or off output registers. But if you write a value to an input pin, it will turn on or off the pull-ups. So what we're going to do is we're going to write a value of 2 to the port B register. Now what that's going to do is, if we look at the binary for that, pull up, there we go. If we look at the binary for that, if we go to port B, we look at port B, 2, 3, 4, 6, 7, 8. So here's PB0, and here's PB1. So it's an input, and PB0 is an output. So this is off. It's staying the same. We're turning it off. That's fine. But by setting it to 2, this is OXO2, we're only setting this bit. So we're turning the port B1 register, we're turning the port B1 internal pull-up on. So that's going to pull that pin up to 5 volts so that the switch will discharge it to 0 volts, so we can get that on-off state. Now, shouldn't have closed that. Let's talk about the third register, the input register, called pin X. Okay, or in this case, it's going to be pin B. So I'll just write B there instead of X. Okay, so the pin register is dynamically updated. You don't have to worry about writing values to it. It's going to receive values based upon the state of all of the pins within that register. So as soon as it gets 5 volts on the pin, it's going to write 1 to that register for the specified bit. And as soon as it goes back down to 0 volts, it'll write a 0 to that bit, and it's easy. You don't have to worry about it too much. So 3, 5, 6, 7, 8. Okay. So normally, again, this is PB1. This is the input. Normally, if the switch is open, if we haven't pressed the switch, so this is open, this is going to be on. And then when we close the switch, it's going to go back down to 0. So we've got to be concerned about that inversion in the code. So just something to think about. What we also have to do is we have to be concerned only with this bit and no other bit, so that if for some reason another bit in the register goes to 1, it doesn't screw up our data. We only care about that bit. How do we do that? We do that by creating a mask variable. What a mask variable is it's a variable of the same length of data you're comparing it to, so in this case 1 byte, that will allow us to extract a specified number of bits out of the entire line of data. So in this case we only want 1 bit, but you can write a mask variable to give you 2 bits, 3 bits, 4 bits, and any particular combination of bits within that data. Now, a mask works by using the binary operator AND. I'll give you the truth table for AND. So A, B, C. Now what a truth table does is it shows you, wow, cannot draw a straight line for my life, is it shows you that for particular inputs, the specified output. So A and B are inputs, C is the output. So 0, 0, 1, 0, 1, 0, 1, 1, 1. So 0 and 0 gives you 0. 1 and 0 gives you 0. 0 and 1 gives you 0. 1 and 1 gives you 1. So that's the truth table. So how does that apply to the mask? So if on our pin B register we have, for some reason, more bits turned on than we need, but still we only care about port B1, we're going to create a mask that lets us pull out only that variable. So what we're going to do, so we're going to create a mask I put that 0 in the wrong, that 1 in the wrong place. Sorry about that. 2, 3, 4, 5, 6, 7, 8. There we go. I can count. So again, we care about this bit. And so this is our mask. And we're going to perform an AND operation on it. So when we do our AND operation, what we'll get is 1 and 0 is 0, 1 and 0 is 0, 0 and 0 is 0, and so on, until we get here where 1 and 1 is 1, and that's 0. So even though all these other bits are turned on, what the mask will do is it will let us focus on specifically that bit. It's a great tool to have. So if not, because it's inverted, so if we push the switch it goes to 0 volts, so it'll turn that PB1 off, and if it's not pressed it'll go up to 5 volts, so it'll, yeah. So if not, pin B, that's the register, and our mask 0x02, because if we go back and we do the binary to hexadecimal conversion, our mask is 2 to the first times 1 is 2. There's our mask. So if that bit is set high, here's where a second Boolean operator comes in. We've got to write out port B to a specific value, but we can't change the pull-up bit within the register, otherwise it'll screw up the rest of our code. So we've got to be cognizant of that fact. How do we do that? Well, it's like what we did with the mask, except we're going to use a different Boolean, different binary operator. In this case, we're going to use OR. So here's the truth table for OR. There we go. So 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. And 1 or 0, 1 is 1. So if we take our port B register, so here's our pull up, and the LED is off, so our output is also off. We only want to tweak this bit. So we're going to create another mask, using the OR, and using this as our mask. So we perform an OR operation. So 0 or 0, 0, 0 or 0. 1 or 0 is 1, and 0 or 1. So we've successfully turned that bit on without affecting any of the other bits. So OR lets you keep that data in line. It lets you preserve the data. So port B OR equals OX01. So that's only turning the last bit on. So that's if you push the button. Else, now this is the tricky bit. What we've got to do is turn it off while still preserving all the data. But if you remember from the OR truth table, if we were to use this OR with the 0 here, it's still going to stay in its on state because 1 or 0 is still 1. So what we've got to do is create another mask using a different, well, not different, we're going to use something other than the OR. We're going to go back to AND. This is where it gets tricky. You've got to think about this a bit. So the LED is on, and we've got to turn it off. So we have to create a mask that's only going to turn this off. So if OR, you can think about OR as preserving data, and AND as destroying data, because if we look at this, you can see 1 and 0, it destroys it, it gets rid of it, it turns it to 0. But it preserves only 1 is the protector bit for OR. So we can destroy this bit by creating a mask 0, 0, 0. Whoops. Almost screwed it up there. Again, 1 is the protector bit for AND. So if there was a 1 here, the way to protect it is 1. So this will protect all of those bits, and this will destroy the last bit. So and it destroys this bit while preserving the pull-up bit, so everything's safe. So if we were to look at this value in hex for this mask bit is OXFE. I got that because this is a good trick to remember, is only the 1 bit is off. So the maximum value a byte can have is 255. 255 minus the 1 bit is 254. So 255 in hex is FF. So 1 minus that is FE. So port B and equals OXFE. And there we go. So you can just go ahead and hit F7. It's done. Open up AVR Dude Assistant. I've got my programmer plugged in and the chip is ready and powered. Again, ATmega 328p, USB, tiny, simple USB programmer. Finish up. And you're going to browse to wherever that hex file is. It's always in the debug folder within the project folder. So if you were to come back to all of your projects, switch LED, debug, switch LED.hex, write, make sure it's on, and there we have it. There we go. So let's go look at our board, see if we accomplished our task.
So we're back at our board. I've turned off my light so that you can see the LED a little better. So what we're going to do is just push the button, and if it works, the LED should come on. And it does. And if I let go, it turns off. So there we go. We've seemingly accomplished our task. So I know this was a bit of a longer video, but I feel like we covered a lot of tasks. We went over the third of the pin registers, so that's the direction, the output, and the input. Talked about how to enable pull-ups. And we talked about getting started with binary operators. Binary operators are a little tricky, but if you write them out and you remember your truth tables, they're pretty easy to solve. It's just like solving any other algebraic equation. You just gotta work backwards a bit. So, this has been Human Hard Drive. Thanks for watching.